Hello everyone, and thank you for participating in our virtual session about next generation rendering technology at Pixar Animation Studios. I am Max Liani, I lead rendering research at Pixar, and later in the session I will introduce Marc Bannister, lead engineer for RenderMan XPU. We are recording this session across two continents. I am in the US while Marc is in the UK. And I guess this is a bit of an advantage that the new digital GTC conference format makes possible. On the flip side, we had to record this session a week in advance, and compared to the normal schedule, we had less time to prepare some of the content that we really want to show. But without further ado, in this talk, I'm going to present RenderMan XPU, what it does and why it is important to us. I will introduce you to the problem space, what it is that we are solving, and we're going to talk about the rendering architecture that we have chosen to take on this challenge. Then I will give the floor to Marc, who's going to present you three among the open problems that we're actually working on, problems we like to see more people doing research toward. So RenderMan XPU is our next generation production renderer. Fundamentally, it is a path tracer and is mainly aimed to produce photorealistic images for movie production, animation and visual effects. I said photorealistic rendering and not predictive rendering. Our goal do not tend to be to produce images that are a faithful representation of a harsh reality. We get fairly close to that, but we allow the artist to bend physics and reality, shaping it at the service of storytelling. And this can be an endless source of troubles, and sometimes it results in that increase in complexity of our solutions. Where is XPU development at? So some parts are ready, in particular most of what is needed for look development, which is the part of production where parts of the scene, including props and characters, are created in isolation and made them look what they are supposed to look on screen. Some other parts of the renderer are now ready, such as a number of features used for computing lighting and final frames. Thinking about light linking or light path expression or advanced light transport features. What we are doing with XPU is to create the next production technology that will take over the existing RenderMan areas architecture. And I'm about to show a clip that shows how our customers have been using RAS. trust us to provide them the rendering technology that is needed for their productions. So thank you. Okay, so what does XPU means? XPU is our abstract term to identify a generic compute device that we leverage in our heterogeneous compute architecture. It is CPU and GPU together, both devices equally capable to produce a given picture, or both cooperating to produce every single frame. It is about to use any hardware you might have on your laptop, on your workstation, your render farm, or over the cloud. XPU produces perceptually identical results across CPU and GPU, and more of this in a moment. But XPU doesn't guarantee an exact match against the current implementation of RenderMan, but it is close enough to be predictive and representative. That means you might look your look development something in XPU and render your final frames in RenderMan RIS if you wish, at least until RenderMan XPU will be fully equipped to render your final frames. This image is to illustrate what I mean by perceptual identity between XPU and GPU. This image was rendered with XPU running exclusively on CPUs. It is intentionally showing some artifacts such as non-converged noise or even stretched textures on the walls and some of the objects. And this is the image produced by the GPU, and they look absolutely the same. So I want to make it simpler for you to spot what the differences are. So pay attention. I'm going to draw some red circles, and the first one is going to be on top left corner. See that? At the center of that circle there is a small firefly, and I'm going to make it toggle between CPU and GPU. Can you see the twinkling? Okay, next. Same thing, another circle on the light fixture on the ceiling. Now toggling. So those are the type of difference you might see. They are very, very small, but there is more of it. This is a full diff between the two images, and it is pretty much almost impossible to see. So I need to brighten it up 100 times. And some of the diffs are caused by bugs in our code. That's perfectly legitimate. And those are things that we are fixing as we are discovering. And the difference is diminished further every month. Some are due to rounding error, which mostly come from different use of instruction between CPU and GPU. For example, fuse multiplying add math, or instruction reordering, or flash to 0. Some of these can be mitigated. It requires a fair bit of effort on our side to isolate the most common reason for differences and forging the code that will produce a closer match. An example is a common cross product. It is a difference of products and is subject to catastrophic cancellation. CUDA will automatically turn part of that math into FMA instruction, while the CPU compiler might or might not. And one code path will benefit from the higher precision, the other won't. And this eventually will change where the indirect illumination rays might hitting, producing the slight variation pixel to pixel that you see here. Under our evaluation criteria, we consider this problem mostly solved in our implementation. And we are at the polishing stage, where we are reducing this difference further and further. Okay, moving on. I mentioned earlier the term look development. I want to show you some of the assets. I wish we had a few more days to finish off the content we want to present on the original deadline. We had to stop earlier, so this is what we have. These images are rendered from production assets taken from our latest movie onward. Disclaimer first, these assets are off-model, meaning they are not exactly as they appear in the movie, and they are out of context. XPU was not used for production during the movie onward because these assets have been developed over the last couple of years, where XPU was not ready to render this. What we are doing here is to source a variety of production assets to exercise and stress the render in a variety of different ways. Testing and validating our tech is important. These assets are rendered in XPU. This is the Barley's Van asset. It is such a hero prop in the movie that the entire scenes are shot inside it. Because it it is a hero asset, it is made of many parts that are meticulously shaded for extreme close-up shots. There are 183 distinct pattern graphs that shades different portions of the surfaces, a large number of very high resolution texture. Some of these are PTEX, some of these are texture atlases, and a lot of procedural noises. These assets load a relatively small quantity of resources compared to a full production scene. Yet this is considered a representative workload. We have a whole section about divergent execution and sorting that type of assets like this produce, and this later on in the talk. This is Barley, is one of the hero character. This asset is developed for extreme close-up with plenty of minute details. Pay attention to the fuzz covered in his skin and clothes. You can see, for example, in his collar, in his jeans jacket, like all the little curves that provides detail. Skin is rendered with path ray subsurface scattering, and we have a whole section about that later in the talk. This is the manticore character, and I'll say this is about fine displacement, hair and fur, and path ray subsurface scatter beneath it. So what is the problem we are working on? Where is it? We should just be able to make the render faster and make it real time, right? We do have GPUs after all. And I wish it was this simple. It's almost never a non-zero sum game. There is always a trade-off. So let's imagine we made an hypothetical RenderMan render engine real time. It's not interactive, it's just full real time, no noise. What would that mean for the user? Well, real time has stringent requirements. Your tech is either real time or is not. It takes very little to fall off that cliff when your assets are complex enough for the scene, for the engine not to be real time anymore. And not real time solutions are flexible. It allows artists to be sloppy when they have to. For example, when they need to create a new scene today, render it tomorrow, and never see that asset again. Real-time rendering assets optimization are absolutely essential, while for us they are beneficial, but not really key. If you strive for real-time, it's because you want to render something many times. And we don't. Our industry renders something once and plays that back many times. It's a very different type of requirement. And real-time graphics tech is often custom tailored to the content, at least as a content creator you're trying to push the boundaries. So your products tend to be the content plus the tech. And we do push the boundaries all the time, but we create tools for mass production. And the final image is our customer's product. So let's see how the artists might feel when we give them a range of different tech, from unusably slow to impossibly fast. Hypothetically, at the horizontal axis we have a frame render time, the time it takes to render a frame completely converged. On the vertical axis, some indicative level of productivity. And the common wisdom is that when something takes way too long, many hours, you cannot be productive, you cannot meaningfully iterate on the quality of your art. And if something takes just a few hours, perhaps you can render overnight. But still, it is an effort. Moving to a tech that renders in minutes starts to be pretty decent. You can iterate several times during the day, refine your work, you start to feel productive. You still perceive productivity though. You are still bound back by a number of tasks that are not rendering related. Moving to seconds and things start to really take off. You feel you're doing the right thing. You can explore the look, you can create better art and get more stuff done during the day. And then if we go to milliseconds, which is the holy grail of rendering, I bet that will feel amazing. But in terms of productivity, it's not very different. Sure, you can see every single intermediate step when you drag a slider up and down, but it doesn't fundamentally change what you do and how you deliver it. Your art won't be fundamentally better. You still spend time loading scenes, you're going to reviews with the art director and director to get your stuff signed off and approved. If the render would be instantaneous, again, it wouldn't change much, it's diminishing returns for most of the application. Now, let's look how much time is spent into preparing those assets, and let's call it overhead. When you expect something to render in days, anything will go, right? Model it, texture it, check it on the farm, who cares? right? Your expectation is convenience and flexibility in the workflow. You're trying to model your process to simplify all that goes into the creation of assets. Rendering in hours is not much different. It's more about the improved technology than it is in the process in creating the content. If you want to render in minutes, now you need to pay attention. You don't overmodel to death, because just in case something's going to be seen in a close-up, you be slightly more careful with your texture. Bake what is really expensive, avoid like extra high resolution texture for light maps and things like that. You want to render in seconds, now you need to care more. You need to pay attention to which asset is visible, you need to define strategies to prune the scenes, to bake things down, maintain those pipelines, maybe you need to combine some of your texture, combine some of your shaders. You need to plan more in advance. You want to render in milliseconds range, overmodeling might not be possible at all. You need level of details to be created and kept in sync. Remember, this is film quality. You cannot afford any popping frame to frame. Anything that passes in games will not be good enough. And some sort of also for the cost of making assets grows. So let's flip that green curve upside down and let's label that as inverse overhead, or the productivity that comes from the creation of an asset. And because we don't need to be real time, in this range, this is where the best value proposition is for the most application. It is fast rendering, still allow for great flexibility and quick asset turnaround. Sometimes we may have technology breakthrough either in the hardware or in the algorithms, and tech in general. Maybe a baking step that was tedious and laborious before is not required anymore, and that range of best value proposition shifts toward the speed. But there are friction forces pushing back, and there might be like ever-growing expectation of quality, or visual effects in every single shot of a production with production time that is constantly shrinking, and this pushes the region back, not forward. So XPU is aiming to cover the stretch between offline, closing up to near real-time rendering. This while delivering final frame quality for movie production. Can it be real-time? Maybe with enough GPUs and relatively static content, perhaps. Some portion of the geometry processing pipeline are not designed for super low latency and real-time application. We still tessellate most geometry to micropolygons. We displace them. We build a finer retracing acceleration structure on super fine geometric representation. That is part of the quality, which at this point in time is non-negotiable with our users and application. And this is not real-time. So that said, XPU is based on a native device abstraction, where multiple GPUs are just multiple devices, such as the CPU is a device. And XPU scale to anything we have tested on, from a laptop with or even without a GPU, to workstation and servers on the farm, and even to special configuration with the 16 GPU, such as the NVIDIA DGX2, which is not even made for rendering. It is designed for machine learning. Still XPU runs on the entire lineup, and yes, we have tested. We have a DGX2, which thanks to NVIDIA, who provided one for us. So moving on, I want to make a pun on some marketing material. And so is this RTX on or RTX off? So pun aside, there is something to be said. RTX on is generally associated with high quality pictures. If you have RTX hardware, you're going to see those sharp reflections and smooth shadows you couldn't afford to compute in real time before. But for us, we already have that quality. It's not a question. So RTX on for our whole industry means faster rendering through acceleration of a portion of the computation. And how predominant that portion of this really depends on the scene content. So RTX on means faster ray tracing. RTX off, we're still getting the same picture. Your render takes a bit longer perhaps. So it is transparent to our users. RTX proposition is almost like a three-state. It becomes a why not? XPU uses RTX, if available, to compute the portion of a scene data that RTX can accelerate. For example, polygons. Everything else is done in CUDA through our robust algorithms. And this is completely transparent to our users. And this is good. If you think about it, it means that you can upgrade your GPUs mid-production and benefit of the improved new hardware without having any effect on the quality and the look. You can submit your rendering to the cloud where you might not have any idea which type of GPU you might get. So switching gear completely now. Moving on to understand why we consider this problem is something to work on. And we need some theoretical digression to make sense of it at all. And for us, the foundation is light transport, which is the physical simulation that underpins the rendering architecture. How does it work? And please indulge me for a minute. First of all, let's turn down the lights. In real life, photons are emitted by some emissive surface illuminating the scene. Some of these photons hit the scene, we frame to the camera. Some might travel far away, not contributing much to anything. Photons are reflected, absorbed, bouncing around the scene. Some more are lost in the process, until some eventually will hit the camera sensor, either imprinting on a chemical film or turning into an electrical signal on a CMOS sensor. A small bit of light contribution is added to the picture in this process, one photon at a time, and we take many billions to have a picture. This looks like a lot of rays, something the RTX hardware should shine at. What's important is the scattering events that contribute to transport light from the emission point to the camera sensor, and we call this a light path. And the entire high-dimensional space that represents all possible paths in a scene is called the path space. Light transport is an optimization problem on how to simulate this efficiently. The math can be easily rearranged to compute light path in reverse, starting at the camera. And it is typical to start exploring the path space starting at the camera. We have GPUs, we can evaluate many light paths at once. But for clarity, let's visualize how we construct a single light path. A ray hits the surface. We need to evaluate manifold for several of the properties of the surface, where it is in space, how it is oriented, what other texture coordinates, partial differential quantities, and a variety of user-defined extra manifolds the user might need for shading. Some objects feature dozens of pieces of data to interpolate. We call these primvars, which is short for primitive variables. Interpolating this data is a relatively complex piece of computation that accesses a fair bit of the data in the process. We then run patterns based off on these quantities to evaluate the surface properties of the object, such things like is it shiny or matte, does it have scratches or stains. And with this, we parameterize a closure referred as a bidirectional scattering distribution function, or BSDF for short. This function allows us to estimate where light contribution might come from by evaluating the exact material response for an input and output direction on a given sampling space. If we know where lights are, we can estimate where the next event contributing might be. We call this next event estimation. Then we scatter to extend the light path, we trace another ray and hit some other objects, such as the glass sphere. I'm going to skip steps, but basically we repeat the process. We might try next event estimation again. Just this time, the BXDF might lead us somewhere else because it's able to respond only to a narrow angle given the incoming direction. And so not all next event estimation computation is actually useful. We may extend the light path again and try next event estimation once more. This time we have a surface in the middle that is occluding, which again, this event is not contributing. We scatter again, and again, eventually at some point we might hit a light source directly, and that would be the end of this family of light paths, or we might terminate earlier because of some criteria, such as like max, like recursion depth or something like that. We need many light paths like these to render a single pixel in a noise-free image. So here it is. This is the rendering pipeline that we compute light transport in the style described before. So you should be able to digest this diagram now and follow the steps. We start the camera and generate rays, we intersect them, we keep only those that actually hit something, and then we sort. Yes, we sort because many rays will hit different geometry types and we need to evaluate their manifolds, and curves behave different than polygons, as an example. And we need the manifold interpolation code to run coherently. So it happens, we progress through the pipeline, we might need to sort in order to run the next bunch of kernels. For patterns, MBXDF, and we're on next event estimation. We use the fair Q to compute shadow rays. Is that orange line that you see? The Q flashes when we reach capacity, and that's a nice trick to improve performance, to work coherent workload. At some point we scatter the path continuation ray, and we go all the way back at the beginning. Is that long arrow that moves back. So do you think that we computed an image by now? Not a chance. We are just here, and we are about to trace this next ray, intersect this next ray here. So this is why we call this a wavefront architecture. We compute, we move forward a whole lot of rays across an entire image and get it to proceed step by step in order to compute the light transport. But this is we also call it feed forward. The render is never allowed to go back and ask for something else that it doesn't have. The data must be flow in one direction. If pattern execution needs some arbitrary user data to be interpolated in order to shade one object, the imported primitive kernels must have computed the data. The rendering pipeline is modular and flexible this way. It can be programmed to implement different styles of light transport, but even more importantly, many of the steps along the pipeline are complex in their own. So the steps, some of the steps can be user implementation. Some are just in time compiled, and we have a lot of these in a scene. So let's take a peek at what we refer as when we say complexity in the kernels. Let's look at one particular material, the Disney BSDF. And this is rather flexible. It's a great shading model. It can describe many materials, and it is popular. People use it. Most render implements this model or their own equivalent. And this is manageable. This level of complexity is not what we consider an issue. And that's not a knife. This is a knife. This is Pixar surface. All of its parameter. Just look at that. This BXDF is used on most surfaces at Pixar in our movies. And several of our customers uses it for their production too. It is extremely expressive, and our artists are fighting tooth and nail for this level of control. At the same time, this is a big challenge for us. The challenge is to extract efficiency out of it. And we have implemented it, and it works, and it is correct. But it kept us busy for some time, and all the while we were thinking sort of, are we actually going to get this done? So, just to wrap up this part of the talk, we are in a challenging domain space where we are asked to deliver uncompromising quality and make it fast. We have a modular rendering pipeline to accommodate for even different style of light transport, and that is going to keep us busy with new challenges. The complexity of it all is growing, is not shrinking. Meanwhile, we have to figure out alternative techniques for features that we know we cannot move forward with. And we are working a fine line between what we can do and the performance we can achieve. What is the implementation technique that lead us there is the question. With this, I want to give the stage to Marc Bannister, who is going to present the next part.
Thanks, Max. My name's Marc Bannister. I'll be presenting the second half of the presentation, which is related to the open challenges we have in XPU. It's important to note that there's a lot of open challenges we have in XPU. So here I will only be discussing the top three challenges that we have at the moment. These are the ones that are causing us the most problems. So the first one is related to sorting and how we currently use it to improve execution coherency and memory coherency. But the effect that has on the rest of the renderer and the problems that we have when we use something like sorting. The second is kernel granularity, so how finely grained do we split up the light transport problem, and consequently how small are the kernels that we launch. And the third one is subsurface scattering, which is a common technique in film production for producing realistic images. However, although it's a simple algorithm and very naturally expressed, it isn't always easy to run the algorithm efficiently on the GPU. So sorting, what are the challenges we have in XPU with regards to sorting? Well, first of all, is it necessary to sort? We do sort an XPU, and I'll go into some reasons why we do this. XPU started off as a prototype. Really, it's developed into a much more production-focused application. There's some key differences today compared to when it first started a few years ago. For example, you can imagine a simple demo or the first version of XPU that we had, the first prototype, it only dealt with triangles. These days we consider a variety of primitives, not only triangles but subdivision surfaces, curves and points, for example. And that means that we need to be able to sort our rays and hit points so that we can intersect and traverse BVHs efficiently, but also to evaluate points on the manifold. Secondly, the original XPU prototype only had a single BXDF implemented. That was the Disney BXDF. These days we have more. I think we have 4 or 5 that we ship with XPU, but moreover we're able to load BXDFs from plugins, so clients can write their own. The number of materials of BXDF is essentially unbounded. Similarly, so are the pattern graphs. So these are the OSL shaders, if you like, that produce inputs to the BXDFs. We can have many thousands of unique pattern graphs that are generated by artists. This is a data-driven pipeline. There's no limitation on how many pattern graphs that an artist might provide. This is more of a problem, even though the number of BXDFs is unbounded. We only expect a few for any given shot. We expect many thousands of pattern graphs. Finally, lighting. So in a simple demo, we may only have a single light source, and maybe that's an environment light. In a production renderer, we expect many different light sources of different types. So for all of these, it's important to sort. We want to sort our big batch of paths by material, by pattern graph. We want to have some sort of coherency to enable us to run lighting. This is very much different to sorting in real-time graphics. Just quickly going through the cases where this might be useful in sorting might be useful in real-time graphics. We need to batch up draw calls based on shaders so that we don't need to change shader state very often. That's important in real-time graphics. Drawing geometry front to back to make good use of the occlusion buffer, Z buffer, alpha blending for semi-transparent objects is another reason why you need to sort. And a lot of this is runtime sorting, but some of this is requires some offline steps to spatially partition your triangles into batches that are convenient for doing these sorts of sorting and re-indexing to allow for better use of the cache when transforming vertices. In a path tracer, we have a very different problem set. Max has been through this data flow diagram, or this flow diagram rather, in detail before. I'll skip a lot of this and just identify two distinct sorting steps. The first one is that whenever we're tracing rays, we want good coherence to the BVH traversal and the primitive intersector. So we find that there's a benefit to sorting the rays before we start intersecting. But and that's fairly well researched, and there's a lot of information about the benefits of sorting there. The less well understood problem is sorting during light transport, or rather direct lighting. We need to evaluate the manifold in an efficient way, and if you've got different geometry types, you need to be able to do that efficiently with minimal execution divergence. We want to sort by pattern graph and by BXDFs to avoid similar execution divergence. So it's important to come up with an efficient sorting algorithm to allow us to do each of these stages efficiently on the GPU without having too much interwarp divergence. So in XPU, we find that we require sorting. Currently, we require sorting for certain steps within direct lighting, but even if we solve those problems, we get a big performance benefit from sorting. However, there's some caveats to this. The benefits that we see, we only achieve with very large batches of paths. I say very large, there's several millions of paths in flight at once, and this is problematic when it comes to the path state. As time goes on, the path state per live path is only going to increase in size, and that's going to translate to several gigabytes of data that we need to have that needs to persist for the duration of the render, just for retaining information about a path. One way of mitigating that is to reduce the size of the path state. There's only so far we can go with that. If anything, we expect the path state to increase in size with time. So the only strategy for us there after that is to reduce the number of paths that we have active at once. If we do that, we need to revisit our sorting algorithms, which are only effective for batches of paths that are at least 1 million in size. So we need to come up with different sorting strategies. So the second part of this presentation is to do with kernel granularity. In XPU, right at the beginning, we decided that, we spent some time analysing the benefits of mega kernels over microkernels, and using microkernels to solve the light transport problem was decided the best approach. This is strongly coupled with sorting. We're able to sort in the intermediate steps for the next part of the pipeline, then we get very good execution coherency and possibly memory coherency when it comes to tracing rays. Further, if we're able to sort the batches for small packets of work within a batch, we can launch kernels to deal with these in a separate stream to overlap the execution of that small amount of work with much larger amounts of work. So there's a lot of benefits that we find for using microkernels. But what are the downsides? Well, here's a small snapshot of an old profile of XPU running a production scene. Not quite production scene, actually. Cut down production scene. And so you can see that we have way too many kernel launches, and this is a problem not only for the fixed kernel launch overhead, but also with the memory bandwidth that we have. This problem is only going to get worse the production scenes that we're going to be trying more frequently, or going to be rendering more frequently, have many thousands of different pattern graphs, which is just going to make the problem worse as time goes on. On a single wavefront, we'll potentially need to deal with thousands of kernel launches. We can't ask our users to simplify their scenes. That's just not the way production works. Artists are there to produce high quality results, and they need flexibility. So this is a technical problem to solve. So we need to explore the space in between single megakernel, which is one end of the spectrum, and very heavy very light and many light microkernels, which is where we've ended up. And we think there's a happy medium, but we need to find out where that is. And the final challenge we have in XPU is subsurface scattering. So what is subsurface scattering? Well, it's the simulation of light scattering aside a volume. In this image, on the sphere on the left has little to no subsurface scattering and is predominantly direct lighting. The one, the rightmost sphere has a lot of light transmitting through the surface and coming out of the bottom of the sphere to the and hitting the camera. That's the subsurface effect. It's very common in everyday materials. A lot of organic and inorganic matter has subsurface type effects. Plants and skin and marble are good examples of these, and milk is an everyday liquid where that can be modelled using subsurface scattering. So why is this feature so important? Well, here are some examples of films. This one has been done by MPC, where they have introduced a digidouble for Rachel in the most recent Blade Runner movie, and the skin in the eyes will have used subsurface scattering to produce the result. And as you can see, it's very close in the results are very close to the original plates, and a lot of these effects are very subtle. You can't get them with simpler materials. There's another example from The Irishman. Al Pacino is a very familiar face. We can't mess around. We need to have a realistic looking result for Al Pacino. And a final image from the same movie is Robert De Niro, de-aged as well. And subsurface scattering can produce some very high quality images. So why is it a problem in XPU? Path trace subsurface is a simple algorithm. It's an iterative loop, essentially, that allows us to find a candidate next scatter position trace array. We use effectively to choose the next scattering position, you evaluate something called a phase function. And then if you don't hit anything, then you did scatter at the next candidate scatter position. So you rinse and repeat. You do the same thing again, choose a candidate scatter position and trace array, and so on and so forth. And as a result, you scatter around inside the volume until you hit the surface, ideally, and where you can evaluate direct lighting. And from that point, you know how much light was transmitted back through the subsurface volume to the camera. So it's quite a simple algorithm to do. If we consider the same problem more visually, you can imagine that a certain subset of the paths for the entire frame hit a subsurface material like the face of a human. However, the first thing to note is that it is a subset of the original path set, typically. Less than half of the original paths we might expect to enter subsurface volume. So not only, before we even start evaluating subsurface, we've already reduced the batch size from something that is ideal to something that is substantially less than ideal. And as we consider the subsurface algorithm, we firstly move into the surface, then choose the first scatter position and trace array. Some of these paths might already terminate, and we can consider direct lighting, but a substantial proportion of them is still active. So we consider the next scatter position and trace array, and further paths exit the material, and so on and so forth. And once we hit depth 4, we find that orbit 2 of our paths have exited the subsurface volume. We continue once more, a further path exits, and now we only have one path that's active inside the subsurface volume. We can continue in this path for a very, very long time and still not exit the volume. And this is not an uncommon scenario in production shots. We see that only a small number of those paths that entered a subsurface material are active after, say, depth 10 or 20, and they may remain active for 100 to 200 iterations, and sometimes even more. So we have a very small batch that we need to consider, and moreover, that small batch is doing something algorithmically simple, but is actually quite complex to compute when it comes to a tracing array. So we achieve great quality with path trace subsurface. The performance on the CPU is good. I presented the challenge that you see today on making it efficient for the GPU. We have some ideas to mitigate these. Hopefully we'll make some good progress and be able to submit or present some of those ideas for next year. So the next steps for XPU, we need to continue supporting the studio as they use XPU more and more. We need to complete some features that we know are missing for the public release, and we need to actually go through a release cycle, bug fix, test, and launch, ideally toward the end of this year, although the date there is to be confirmed. Then the next big things are volumes, which is something that's a necessity for a large portion of production shots. And we need to investigate incorporating some more sophisticated light transport mechanisms into XPU. So thanks to NVIDIA, who have helped us out with the development and performance of XPU. The RenderMan team, with whom XPU just wouldn't exist. There are so many members there that have really helped with the development of XPU, the entire team, in fact. So Pixar Studio Tools and Pixar Production for their help in integrating XPU into the studio and allowing us to try XPU out with production assets. So this is where I take some questions. Hopefully you can send those through the medium NVIDIA suggests and we'll be able to answer. Thank you very much.